All right, college algebra students, this is Dr. Demery again, working with section 5.5, exponential modeling. And this will be the last lecture for this module or section, chapter, whatever you want to call it. And so we've been working with exponential growth and decay for a while, and this is what this is all about. You're trying to figure out, like when things like, for example, like population grow, all right, it happens on an exponential level. So what happens is that it ends up doing something like this. And what we have to do is find out at what level it's growing and for how long it's growing, and then what is future projection and initial population. Those are all the variables that can come involved in these things. So when we talk about that, the projected value or amount of an item or number of populational growth or people or animals or whatever, we say that that's A. And then we say that the initial value of the population is A sub naught. And then we go ahead and also indicate that there is a projectile value that we use. It's E, and E has a certain property to it that allows for continuous evaluation. It's the moment of instant evaluation. So it's a concept, and it's actually a value. If you punch it into your calculator, you can see what value it is. All right. So there is, if you go ahead and type in second e to the first power. All right. That's hard to probably see if I hopefully can get it to look better, but that's going to be hard to see it. But if you evaluate it, yeah, it's really hard to see. It looks like this. I just wanted you to go ahead and see. You can evaluate it. All right. So you can go ahead and put it into the calculator as e to the first power, and it'll equal this 2.72 approximational value. So E has a unique property to it. Like I said, it allows you to instantaneously grab growth model value. So now what we do is we raise E to some K value, because K is actually our growth value, whether it's going up or down. It could go, if it's negative, it's going down. If it's positive, it's going up. And then of course, time exists for it to happen. So if it's growth, it's going to be positive, as I said. K is going to be positive. All right. And um, if it's not growth and it's decay, then it'll look something like this. All right. It'll look something like that. And that is when K is negative. I'm just going to put K is negative up there. All right. Now, right now, these first couple questions, this one particularly, okay, we are only but asking the student to be able to understand these parts and then understand how to run this equation. And they say that P represents the population. All right. And I'll say that this is future projected value system for A. So the amount of whatever item you're talking about. That's why I use the letter A. Now it says, what is the population of Port St. Lucie in 2020? Now it's always going to be A sub naught. A sub naught is the initial value. Okay. So then this is pretty easy. It's going to be the 195, 885. So that's the answer we're looking for there. It's always this number when they ask you for the immediate. It says, in what year is the population of the projected to reach such? So now they're making you go ahead and find out in what year means they want to find out, they want you to find out how many years, so how much time passed, and then add it to 2020. I think we did one of these problems in the other lesson that we just looked at. So we're going to go ahead and isolate for that value. Now, if we are trying to find out T, let's take this equation and not even worry about the numbers. Let's just take and isolate this equation. how do we get this t by itself with just these, and don't worry about the 195,085 and all, 260,527. Let's not worry about any of that yet. Let's get this by itself. So how to do it? So you want to divide both sides by a sub naught. So it's going to be a divided by a sub naught. And then when we have that, we have e raised to the kt power. Now, in past lessons, we talked about how to control exponential power involving this component. And we can control it by the power rule that's associated with logarithms. All right. So what we could do is, because e is what's being used, is we could think of ln, because remember, ln is log base e. So if we ln both sides, and then we ln this side, and this is going to be a little tight, so I don't like what I'm about to do here. If we ln both sides, then I'm going to get this right here to allow me to pull the kt to the front. So watch this. It's going to be ln of a divided by a sub naught. And then it's going to be the ln and the e. I'm going to show you here. The kt drops down. And actually, I'm going to put the kt. Remember how I said you pull it in the front? I mean, it doesn't matter. You're going to put it in the back. But we're going to put kt in the front and then put ln of e. And what do we know about ln of e? ln of e is 1. All right. So this basically goes away. Now, that means that you can solve, and this is very important. This can go one of two ways. You can go ahead and solve for t or k based off of this formula right here. Just a matter of which one you want to divide by, here. So if you want to find out k, which a lot of times you do, you're going to go ahead and take ln of projected value divided by initial value, all divided by t, how long it takes to get to that k. Or if you want to go ahead and find out time, which is in this case what we want, because we already have k, then we're going to go ahead and put t is equal to ln of a divided by a sub naught divided by k this time. And so now what this question right here is asking for is in fact utilizing this formula. Okay. It wants us to know how long it takes. And then we're going to add this t that we're going to come up with back to 2020. So what you do is you take your calculator, all right, take the trusted calculator and start putting in the numbers. Okay, I'm going to go ahead and focus on this. Now, this is what we're trying to fill in. So, ln, all right, first of all, let's use alpha, y equals, and let's get that fraction going. And then what we're going to do is hit ln, and then we want another fraction. So we want to put a fraction on top of fraction, it seems. But then we want to take the projected value of 260,527, and then we want to divide that by the initial population of 195,885. All right, and then we want to go ahead and close that parenthesis, dive to the bottom, drop down to the denominator, and then we want to divide it by the k value. All right, here. So what we're going to do is find that on here, and it's going to be 0.01833, because that's what's already on the screen. I didn't make that number up. It's right there. All right, it's pretty much right part of the problem. All right, so now I hit enter. So then it's rounding to the solution to the nearest whole number. So this is going to be basically then 16 years for that to happen. So you take 16 years and you say that that's our answer. It's going to take 16 years for that to happen. But they didn't ask us that question. They said, what is the year in the population? So what you do is take 16 and add it to 2020. So we get 2036 is when that year will happen for this projected value to occur. And there we have our answer. All right, pretty simple. When you have this formula, please get those onto your, memory banks, or get it into your, notes, and then use it enough. And then when you get to taking the test, you'll know which one you need. And we're going to go ahead and use this one in a second. We're going to look at what half-life looks like, what does double life look like, and all those things. So let's take a look at a couple other questions. So here is the formula that they give. It's the same formula as I given. They changed the y to, or excuse me, my a to y. Who cares? All right, it's the same exact formula. So it says the exponential growth function that models the population of Okeechobee is blank. So now they're going to obviously give you some value here. Okay, the population of Okeechobee was 5,514 by the 2020 U.S. Census. All right, found that the population of the Okeechobee had grown to 6,496. So the initial was this, the projection was this. What was the growth factor? So the thing is that we have a couple pieces of information and we need more. All right, because now it was 2010 when it was 5,514, and then 10 years later it went up to 6,496. So what would the K be? And that's when you would use this guy right here. So you're going to go ahead and find out the K value, because it does not give you the growth factor value. It doesn't give you the percentage of growth. It only gives you the numbers. So what you have to do is, and see, I love my formulas that I'm giving you. So it's ln of, now we're talking about the projected value is 6,496 divided by the initial value of 5,514, and then we're going to divide that by the years, because remember it's years here, and we're going to put in 10 years because that's how long it takes to make that happen. Now, you know that this is growth, right? You know that it's growth because the projected value is less than the initial value. So if the numerator is greater than the denominator, then you have growth. On the other hand, if the projected value is less than the initial value, you have decay. And that should make sense in your mind, right? If something's in the future is going to be less, then it must be, something must be killing off the population. One thing that could be a worrisome thing, that some people are worried that not enough people are having enough children to sustain the population growth. So it's going to decline right after, like, the baby boomers and everything, they gone, and then you have, the next generation of people are being very conservative about having children. There's going to be very much a decline in the population, which could be threatening to civilization. So those are things that are interesting. Okay, but anyway, we're just using our calculators at this point. So I like to go, since it's already set up, I like to come back into my old one and just use it. So I'll show you how I do that. I go ahead and I went up to here and hit enter. And once I hit enter, this comes up. Now I want to modify this, right? So I'm going to go ahead, and maybe it's not worth modifying or doing it all, but I like to just take, and since it's all set up for me, I just like to replace my numbers. So I just hit delete, 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 and I'm putting in my numbers. So 5514 for the denominator. Come up to my numerator, delete, 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 delete. Just delete it until it's done. And then I put in my 6,496, and then I hit enter, and then I get some value. All right. So what does that value mean? So if I move my decimal point over 2 times, 1, 2, that's 1.6% growth. Okay. But it says right here, it says where t is the number of years since 2010, write the exponential function growth study model Okay, the exponential function model, and it says 4 significant digits. So I'm going to go ahead and show you what 4 significant digits means. All right, the 1639 is most significant digits. The zeros aren't adding significant digits. So we go ahead and have it as 0.01639. All right. So now you can finish, or you can write your entire equation as now future value or future population is melded by the value of the initial, which is the 5,514, with e raised to this new percentage value that we come up with, which is the 6 or the 0.01639, with now the t value, and we could say now how long will it take. See, here's the thing, is that the model predicts the population Okeechobee in 2029 is saying, well, from the initial value of population, okay, we're looking at the model is predicted that the population in 2029 will be blank. So we're looking at future projection of this. Now, how much time is that from 2010? So we're looking at 19 years, right? 19 years from that time period. So what we do is we can put in t as 19 and get our answer. So we're taking 5,514, and then we look at ln, so second ln, it's going to give us e, and then we have the 0.01639, and then that's going to be 19, or times 19, to give us our answer. So we're looking at 7,528 people, and it says round to your solution to the nearest whole number. So we're looking at 7,529. So that's the answer we're looking for there. Okay. Now it says determine the year that the model predicts the population of the Okeechobee will be 9,568. So what we're doing again is doing this guy right here. So we're modeling this again, and we're now having the value system of the projected value A as now a new number, 9568. So I'm going to go ahead and come up here, and I'm just going to hit enter because it's the same setup. So I'm going to go ahead and change some of my numbers here. So some of my numbers is 0.01639. All right, that's changed that. And then I'm going to come in here, and I'm going to delete all that. And I'm going to put in my 5,000. That's my initial 5,514. And then I want to go ahead and say, well, what will happen when I go ahead and equal what 9,568. All right. I think you like when I show you. I'm sorry. I'm trying to do all the work and operate too many things. All right. So now you have some idea about what I want to put in there. Okay. Now that means that it's going to be 33 years. And what do they want? The nearest whole year, right? Round solution to the nearest whole number. So we're looking at 34 years from 2010. So if you can't do that mentally, you can just, I mean, that's pretty simple. But anyway, 34, and then we just go ahead and do that, right? So we have 2044. 2044 is when that's going to happen. All right. So the reason why there's only 12 questions in this, there's only 12 questions for this homework, is because you have so many parts, and you have, like, you see how I'm explaining in great detail these things. Okay. Now let's go ahead and see here. I got to talk about this one perhaps. It says right here in this particular problem that E. coli is under ideal laboratory conditions when the bacterium is grown in a nutrition-proof medium. All right, the number of cells in the culture doubles approximately every 24 minutes. All right, every 24 minutes, this thing is doubling. Okay. Now, we know that we're talking about it says approximately how many bacteria will be present. So we're looking at the exponential growth model here. It's growing. It's doubling. Okay. Now, we don't know what suppose the initial colony is 400 E. coli bacteria are being used for the experiment. Use the exponential. So we're looking at exponential growth model to represent this, but we know that we need to find the growth factor. Now, time is relative to, mostly we speak of time in respects to, days or years. That's what we normally talk about with respects to time, but this is forcing it into minutes. Okay. So now when we're looking at that, okay, that time is that. So we're going to get some of these pieces, right? And we're looking at time in minutes. We're looking at this model in respects to 24 minutes. So we're going to take this model, and I keep on pointing at it, but you can't see what I'm pointing at. We're taking this model and representing it. So not this one, but this one. Okay. We need to figure this out in respects to minutes, because it is talking about minutes. But wait a second. When we're talking about doubling, that's taking the initial value and doubling it, right? So we're looking at taking the projected and doubling the a sub naught. So whatever the value of a sub naught is, we're going to double it. All right. And then we're going to have that is our way of handling the value system of doubling. Okay. Now, again, it's growth. So we know that the numerator should be greater than the denominator, right? So this is what we're looking at now, and we're talking about time. So now, if we go ahead and look at this, okay, we know that a sub naught knocks out a sub naught, right? I mean, isn't that just common understanding of the value system? So when we're looking at doubling, then all we have to do is take ln of 2 and divide it by t. So this is our growth model that is involved in doubling something. So this is our formula that we're going to be looking at, okay, for doubling. And half-life works the same way, okay? Half-life is 1/2 of the initial. So this would be 1/2, and then the a sub naughts knock each other out. So you have ln of 1/2. So that's how 1/2 works as well. So that's in decaying function. Now what we want to do is take and put in our pieces again. So we're trying to find out k. It's going to be the ln of 2 divided by 24 minutes. All right. And we know that this is dealing with minutes. Okay. So we're not, we're because if it asks you, look at later on, it says 200 minutes. They're going to keep everything in respects to minutes, not years. All right. Time is measured in minutes in this particular function. So we're going to look at this by taking our function and doing ln of 2 divided by 24. And we're looking at our growth value system of 2.9%. All right, 2.9%. Now, when we look at our answer, we're going to go ahead and do much of what we did before. We're going to write the initial value of 400 with e raised to 0.02888 because it wants 4 significant digits, and then it'll be t, and see what we'll model right here. Okay. So what I just verbalized is what's being demonstrated here on the screen. Okay. And again, I'll write that down if you can't see it very well, but the projected amount is going to be 400 times e raised to the 0.0, and then it's 2888 t. And remembering that t is measured in minutes. Okay, and it'll tell you that, right? It should say that within the problem. I do. Okay, it doesn't say that in the initial problem, but it says it right in the ending here. It sometimes does tell you recorded in minutes. Okay, so now we have the growth model says approximately how many bacteria will be present in the colony after 200 minutes. So then all they're asking you to do is to change T to 200, and dropping in T for 200, you can use your calculator to do that. Okay, and since it's so clear there, I'm going to do that. So I'm going to take 400 times, well, I don't really need to do the times. I mean, matter of fact, I'll just do 200 or 400 second ln gives me E, and then 0.02888. All right, there's 4 of them, or 3 of them, and then I'm going to go ahead and do 200 minutes, so times 200. So now we're looking at this at 128,987, because we're looking at the nearest whole, right? Nearest solution whole number. So it's going to be quite a bit. I mean, it's going to be the 128,987. Okay. Darn it. I lost my clearness of the image. So all I did was drop it in the calculator. Okay. Everything is dependent on using the calculator, as you can see. Now it says the bacteria colony will reach a population of 1 million after blank minutes. So they're asking us to find T again, meaning they're asking us to run this population value, and then the initial is 400. The projected value is, the initial is 400. The projected value is 1 million, and so it is. We use the calculator to generate how much time is needed to go ahead and create ln of the initial of 400 with 1 million projected. All right, there you go. And then all divided by K, which K is the 0.02888. I am so happy to share with you these particular formulas. So you should be definitely locking in and appreciating these formulas that I'm giving you right here. All right, these are the most important formulas that can just help you just throw the numbers in and get your answer. Now you probably are frustrated with me right now thinking I'm going too fast. You don't know how to lock it in to just put it where to put the numbers. That's what you're confused by, and you'll get there when you just associate with what I'm going over. And I'm telling you, rewind it a couple times and get the feel for where I'm putting the numbers, because I'm articulating those number systems, and all I'm doing is using my calculator. And in all honesty, I know all this stuff in my head. I wouldn't even need to write any of this stuff down, and just punch it into my calculator. I'm done. I'm whipping these problems out with no problem because I'm using my calculator. I wouldn't be going ahead and doing all this stuff, because I would say, well, I know it's going to be ln and all that other stuff. Well, I don't want to have to do the whole concept of punching it in, so I'm going to do that to myself. All right. Once I go ahead and drop it in, I'm going to go ahead and put in the numbers. It's going to be, all I'm going to do is take this number, change it to 1 million. Remember, it's always projected value goes up there. All right. The initial is 400. And then the culture, the cultural value to do that is 2888. And then I'm done. So it's going to take 270.9, or remember, this is minutes. 249, let me see what rounds in here is whole number. It's going to take 271 minutes for that to happen. Okay, after 271 minutes. Now watch this. I'm going to show you something. Okay, so this is 271 minutes. All right, never mind. They didn't do something tricky on you. Okay, so I'll leave it at that. So this is what we're looking for how to get the answer. I'm trying to keep still on that. All right. So this is a matter of using the formulas that I've given you. Now, one thing that they're going to talk about is half-life. Radium, and this is right here, half-life. Okay. I know, okay, that these problems are surrounded by the same exact concepts. This looks like a lot of noise, a lot of reading, okay? I don't care. I'm going to be honest with you. I barely even, I've never seen this question in my entire life. I've never seen this problem. I know that I see radium. I know that and then they say it has a half-life. I'm looking for words that are critical, like either double life or half-life or something like that. I'm looking, like they do that for what else? Bone deterioration and you know, radioactivity. They have all kinds of variety of different component problems that involve decay and stuff. So anyway, for question number 5, okay, I'm looking for blank years are required for the original amount of radium-226, all right, on Madame Curie's remains to reduce to 9.3% of its original amount. Okay. Now, first of all, I need to come up with an equation. All right. And the thing that I'm looking at is that the half-life of it takes 1,600 years to happen. Half-life, meaning whatever's there initially, it's going to take 200, or it's going to be 1,600 years to become half of what it was. So immediately whenever I see half-life, and I'm trying to keep these on one singular page so you can really appreciate it, all of them together at one time, is that once I go ahead and do this, I want to come up with K at half-life. I don't have to worry about too much. I'm just going to go ahead and follow what I have here, and I'm just going to do, instead of 2, I'm going to put 1/2 divided by time. All right, that's a half-life, and it gives you the half-life number of years. So you're just going to take ln of 1/2 divided by 1,600, and we're done. So I'm going to take my calculator. I love these word problems dealing with half-life and double life, because ln of 1/2 divided by 1,600 is really a really easy way to find K. So ln, and I like to do the fraction, so I'll put it as a fraction. ln of 1/2, and second. So there's my ln of 1/2, and then I'm going to go ahead and divide it by the number of years that it takes to get one half-life, so 1,600. And then that's the number system that we're looking at. Okay. Now, you might be wondering, what does -4 mean? Okay. It means you back off the decimal for 4 times. So in this respect, if it's that, then we'd have 0.0004332 if we're talking about 4 significant digits. All right. Now, that is if we were using 4 significant digits. All right, so we have this for our value system of our K for half-life. Now it gets into, all right, and how many years are required to get to 9.3% of its original. So we already now have its K value. So I'm going to come back. I'm going to have to come over here. All right. Now, we don't know what the initial value is. Okay. So what we do is we say that we don't care about the ace of knots in this particular case because we're asking for the 9.3% of its original amount. So now we can represent that as 0.9 or 0.93 equals, and then we have this e raised to this 0.00043332 t, okay? And all we have is one variable, and that's what we're solving for. So what we're going to do is take ln of both sides. So we're going to do ln of 0.093, all right? And then we're going to divide it by this right here, this 0.004332, and that's going to give us our time. So let's take a look at that. And by the way, I've been putting this is negative, by the way. So we're going to put that as negative. And that came about because it says negative right there. Okay. Now, I go ahead and punch that into my calculator, right? So I'm going to go ahead and do ln. It got so bright. All right, so I'm going to do second alpha. I'll focus in it when I'm done punching in, but ln of 0.093 divided by negative 0.00043332. And then that's going to give us 5,482, and it says round to the nearest whole. So it's going to be 5,483 years is how long it's going to take for Madame Curie's remains to be at this percentage. And there's our answer. All right, 5,483 is exactly what I said. All right, and for your focus on what I punched into the calculator, all right, there's the focus. So you know what I'm punching into my calculator. So then, I wish I can keep it still, guys. I'm sorry. But anyway, there it is. It's pretty fascinating how fast this is. That all that reading looked like it was just nothing but a bunch of nonsense to me. The heart of this was just two things. Was this formula right here, and then using that formula to generate our answer. It's pretty powerful. All right. Now, these problems work in respect to exactly those things that I've just gone over with you. Okay. So I'm going to, you've got to really get into the heart of it. I went over some significant pieces, and you've got to get that into your head. And that is, you've got to get into these four formulas that I've now went ahead and bolded for you. Once you get that, man, is it easy. The problem set is actually really easy. All you're doing is managing between these formulas. Which one to use? Double life, half life. Oh, you got initial and a set populational value. What is our growth or decay percentage? And so you get all these different outcomes based off of these four problems, and they answer all your questions for you. All right. So I really hope that's what you need. I know I personally enjoy the heck out of this. It's just if you're really fired up on it, all you're utilizing is this formula at its best. All right, right there, and you're knocking out these problems. Okay. I will leave you to figure out the rest of this. Okay. And if you have, hey, there's Half-Life again. Woo-hoo. All right. So I'll let you go ahead and work on it. If you need me, just reach out and I'll assist you independently. All right. Good luck with your studies.